February 14, 1943. North Atlantic Ocean. 3:17 a.m. The depth charge detonates 40 meters beneath the surface. The shock wave slams into U-442's steel hull like a freight train hitting a tin can. Inside, men are thrown from their bunks. A valve bursts. Seawater sprays across the aft torpedo compartment. The lights go out. In the darkness, someone screams a name that nobody answers. Above, HMS Totland circles. Her sonar pings. Nothing. The U-boat has gone silent. The commander has killed his engines. He is waiting. He knows the British will give up in 2, maybe 3 hours at most. He has done this before. He will do it again. He is wrong. But not for the reason he thinks. Because 7 hours later, U-442 will surface with her hands raised, forced up not by depth charges, not by sonar, not by any weapon the Kriegsmarine had trained them to defeat, but by 300 meters of weighted British steel wire that cost less to build than a fishing trawler and had no electronics, no explosives, no radar whatsoever. By the time this story ends, that wire will have trapped 10 U-boats, helped reduce German submarine effectiveness by 41%, and saved thousands of merchant sailors who would have otherwise drowned in the freezing Atlantic. And the man who designed it, a 47-year-old cable engineer from Newcastle named Arthur Willoughby, who had never served a day in the military and whose idea was rejected 3 times before anyone would listen. Stay right here, because what you're about to discover changes everything you thought you knew about how Britain won the war at sea. Let's go back to where this nightmare began. 1942. The worst year of the Battle of the Atlantic. 6 million tons. That is the weight of Allied shipping that sank to the bottom of the ocean in that single year. 6 million tons of food, of oil, of ammunition, of the blood and steel that a nation fighting for its survival cannot afford to lose. Rendered in ships, that number is 1,664 vessels. Rendered in men, it is tens of thousands of merchant sailors who went into the water and did not come back out. Winston Churchill, a man who had stared down the fall of France, the Blitz, the fall of Singapore, would later write that the only thing that truly frightened him during the entire war was the Battle of the Atlantic. Not the bombs falling on London. Not the German army standing at the English Channel. The submarines. Always the submarines. Standing at the center of this disaster, invisible patient. Lethal was a weapon the British had no reliable answer for the Type 7 U-boat. Roughly the length of 2 city buses, crewed by 44 men, capable of diving to 200 meters, and sitting there in absolute silence while the destroyers above hunted uselessly. The Germans called the period between 1940 and 1942 Die glückliche Zeit, the happy time, because that is what it was for them. A massacre conducted in slow motion, convoy by convoy, month by month. While Britain bled, the British had ASTIC. That is what they called their sonar system, developed after the First World War. A pulse of sound sent into the water that bounced back when it hit something solid. On paper it worked. In the North Atlantic in winter, in the acoustic chaos of a 40-ship convoy, with every propeller churning the water into white noise, it was nearly useless. A skilled U-boat commander could dive beneath a thermocline, a layer where water temperature dropped sharply and bent sound waves away, like light bending through glass, and simply disappear. The ASTIC ping would curve away harmlessly into the deep. The British destroyer would circle and find nothing, while the submarine sat 80 meters below. Lights-dimmed crew, breathing quietly, waiting. They tried depth charges, but depth charges require you to know where the submarine is. If your sonar cannot find it, your depth charges fall into empty water. They tried more aircraft, but aircraft cannot see through 50 meters of ocean. They tried hunting submarines in packs using coordinated search patterns. The U-boats adapted. They attacked at night on the surface where ASTIC was almost completely blind. The escort commanders were experienced, brave, and increasingly desperate. Every answer they found, the Germans had an answer to the answer. By the winter of 1942, the mathematics of the Atlantic were pointing toward catastrophe. Britain was losing ships faster than it could build them. The oil reserves that kept the Royal Air Force flying, and the factories running, were falling by the week. Churchill's advisors ran the numbers and presented him with a timeline. If the rate of sinking continued, Britain would cease to be a functioning military power within 18 months. Something had to change. But nobody, not the admirals, not the scientists, not the engineers, could agree on what that something was. Nobody. That is, except for a quietly spoken mechanical engineer from Tyneside, who was about to suggest something so blindingly obvious, so laughably simple, that the first 3 committees who heard it sent him home without a second meeting. Arthur Willoughby was not a military man. He had never served. He was 47 years old in 1942. Heavy-set, fond of pipe tobacco, and more comfortable with load-bearing calculations than with admirals. He had spent his career laying telegraph cables along the seabed, understanding in precise mathematical detail how a weighted steel cable behaves when it is dragged through water at different speeds, different depths, different angles, how it spreads, how it sinks, how it holds position against current and drag. This was not glamorous knowledge. Nobody wrote newspaper articles about it. Nobody gave speeches about the heroism of undersea cable engineers. But Arthur Willoughby understood something that most naval officers did not. He understood that the ocean is not empty. It is a 3-dimensional space, and if you fill enough of that space with enough steel, something moving through it will eventually touch what you have put there. He had watched ASDIC fail, read the convoy loss reports, sat through 2 evenings of BBC broadcasts describing the latest sinkings, and arrived at a conclusion so straightforward that it made him angry it had not occurred to anyone sooner. Stop trying to find the submarine with sound. Find it with wire. The idea came to him, not in a flash of inspiration. He would be skeptical of anyone who described breakthrough thinking that way. But over the course of 3 weeks in late 1941, working with graph paper and tide tables at his kitchen table in Newcastle. The mathematics were not complicated. If an escort vessel towed a long cable at the correct depth, spread laterally by a system of underwater paravanes, essentially weighted hydrofoils that used the ship's forward motion to pull the cable outward, like wings, the cable would create a vertical curtain in the water. Not a net, not a barrier, just a curtain of steel that hung in the column of water at whatever depth the submarine preferred to operate. You did not need to detect the submarine. You did not need to know where it was. You simply needed to be moving through the same water it was moving through, and your cable would find it before your sonar would. Contact would wrap around a propeller shaft, snag an external antenna, stress a weld seam on a ballast tank. Not enough to sink the boat immediately. Enough to make depth dangerous. Enough to make the commander choose between surfacing and drowning. Enough to win. Willoughby put his calculations into a 12-page document and presented it to a regional naval office in January 1942. The officer who received it thanked him politely and told him it was an interesting amateur contribution. The next committee he reached through a contact at the Ministry of Supply sat with him for 40 minutes and then explained that the concept, while creative, faced insurmountable engineering challenges and was not a priority area of research. The third man he spoke to, a senior figure in the Admiralty's procurement structure, whose name does not appear in the available records, told him directly that the Royal Navy was not in the business of fishing for submarines, and suggested he return to his cables. What none of these men understood what Willoughby was too junior and too civilian to explain convincingly was that he had already done the engineering. He was not proposing a concept. He was proposing a solution with the calculations attached. He did not go home. Instead, he made a 4th call to a contact he had worked with on a pre-war post office cable project, a man now working within a department of the Admiralty, with the deliberately forgettable name of the Department of Miscellaneous Weapons Development, the DMWD, an organization specifically created to hear ideas that regular procurement channels had already rejected. Willoughby was given an appointment for the following Thursday. He took the train to London with his 12 pages of mathematics, a box of pipe tobacco, and very little expectation that this meeting would go differently from the others. It did not start well. The two DMWD engineers in the room were polite, but visibly skeptical. The paravan geometry Willoughby proposed was not a new concept. Paravanes had been used since the First World War for minesweeping. The question was whether a cable system based on that principle could maintain consistent depth and lateral spread across the range of speeds and sea conditions that an actual Atlantic escort would encounter. Willoughby's response was to open his calculations to page 7 and begin working through the hydrodynamic load distribution numbers. 2 hours later, one of the engineers asked him if he could be available for a trial at the Firth of Clyde in 6 weeks. Willoughby said he could rearrange his schedule. The first trial, conducted in March 1942, using a converted minesweeper and a decommissioned submarine hull anchored at 45 meters, produced results that were simultaneously encouraging and deeply frustrating. The cable system made contact with the target on 3 of 5 passes. On the 2 failed passes, the cable planed upward at speed, losing depth coverage. The paravanes were stable, but not stable enough. The effective operational speed window. The range of vessel speeds within which the system functioned reliably was narrower than Willoughby had hoped, 4 to 8 knots. For a fleet destroyer, this was unworkably slow. For a convoy escort corvette whose normal operational speed in bad weather was 5 to 7 knots, it was almost exactly right. Willoughby spent the next 6 weeks in a shed near Greenock with 2 Navy machinists redesigning the paravane geometry. He added a trailing edge camber that improved stability at low speed. He adjusted the cable weighting profile so that it maintained depth more consistently against varying drag. He ate badly, slept on a camp bed, and mailed his wife a postcard telling her the weather was fine. It was not fine. It was Scotland in spring. The second trial in May 1942 produced contact on 7 of 8 passes. The one failure occurred in a sea state that would have grounded most small vessels anyway. The DMWD engineers watched the results, looked at each other, and then at Willoughby. One of them said with the characteristic British understatement of the era that this appeared to be showing some promise. By June 1942, a refined version of the system had been approved for limited production and operational testing. The paperwork referred to it as the Anti-Submarine Towed Cable Device, Mark I. Nobody gave it a more memorable name. Nobody threw a party. Willoughby was thanked, given a consultant's retainer, and told he would be contacted regarding further development questions. He took the train back to Newcastle and told his wife he had been working on cable problems. This was true. The first operational systems went aboard escort vessels in the late autumn of 1942. The corvettes and frigates that received them were given minimal documentation and brief verbal instruction. The system was simple enough that this was adequate. A cable drum mounted at the stern, a pair of paravanes deployed over the side, a simple depth gauge to confirm the system was riding at the correct level. No electronics, no maintenance manual thicker than 8 pages, no specialist operator required. The U-boat commanders who were operating in those convoy lanes in the winter of 1942 into 1943 had no idea any of this had happened. They knew about ASDIC. They had been trained to defeat ASDIC. They had been briefed on radar on pattern-of-life analysis, on the increasing use of airborne patrols. Nobody had briefed them on wire, which is why when U-442 finally surfaced at 5:44 a.m. on February 14, 1943, 7 hours after her commander had been certain he was safe, the crew who came up through the conning tower hatch blinking into the gray Atlantic dawn were not prepared for what they found. HMS Totland was 600 meters away and already at action stations. The U-boat's deck gun crew reached their position and then stopped looking at the destroyer bearing down on them and then at each other. And then they put their hands up. What had gone wrong below took the British intelligence officers 3 days of prisoner interviews to fully understand. A propeller shaft bearing had begun to run hot 6 hours after the escort passed over them. Then a weld seam on the port ballast tank, stressed in a way the crew could not immediately account for, began to weep water at anything below 60 meters. Diving deep, the commander's primary escape route had become impossible. Staying shallow meant staying within range of depth charges. Surfacing meant capture. The mathematics of the situation had one answer. The commander, a 31-year-old Kapitänleutnant from Hamburg, who had successfully evaded British escorts on 11 previous patrols, could not explain what had happened to his boat. There had been a vibration, he said. Early in the night. He had assumed it was wave action. He had assumed wrong. In 6 weeks, it would happen again and again and again. But in those early hours of a February morning, with U-442's crew standing on the deck with their hands raised and the cold North Atlantic wind cutting through their leather jackets, the weapon that had beaten them was already sinking back toward the depths behind Totland's stern. Unremarkable, silent. Exactly 300 meters of weighted British steel wire, waiting for the next one. What nobody knew yet, not Willoughby, not the DMWD engineers, not the escort commanders filing their reports, was that word was beginning to reach the German Naval High Command. That something was happening to boats operating in certain convoy lanes. That submarines were surfacing in conditions that made no tactical sense. That commanders were reporting damage they could not explain. In Berlin, the men responsible for U-boat operations had begun asking questions that nobody had answers to. And in the coming months, those questions would drive a response that would test the cable system to its absolute limits and nearly end the entire program before it could achieve its full potential. Because what Willoughby had not calculated, what no one in the DMWD had fully anticipated, was what happens when the enemy stops being confused and starts being angry. In Part 2, we go inside the Kriegsmarine's desperate attempt to figure out what was killing their submarines, and the moment a captured British escort nearly handed them everything they needed to shut the entire program down forever. Last time, Arthur Willoughby, a cable engineer from Tyneside, nobody had ever heard of, walked into the Admiralty with 12 pages of mathematics and an idea so simple it was almost insulting. No electronics, no radar, no sonar. Just steel wire dragged through the ocean at the depth a U-boat liked to hide. By February 1943, it had already forced U-442 to the surface. Crew hands raised. Commander speechless. The cable had worked. The question now was whether Britain would actually let it. Because here is the number nobody talks about when they tell this story. Between January and June 1943, the Admiralty received 23 separate proposals for new anti-submarine technologies. 22 of them received immediate funding review. The towed cable program received a letter asking for additional documentation. While men were dying in the Atlantic at a rate of 900 per month, the bureaucracy was asking Arthur Willoughby for more paperwork. And this is the moment when everything nearly collapsed before it could begin. Rear Admiral Geoffrey Hardcastle was 58 years old and had spent 34 years in the Royal Navy. He was not a stupid man. He was not a coward. He was, however, a man who had built his entire career on a specific understanding of how naval warfare worked. And Arthur Willoughby's cable device did not fit that understanding in any way that Hardcastle found comfortable. When the DMWD forwarded the cable program file to Hardcastle's Anti-Submarine Warfare Coordination Office in March 1943, requesting formal fleet approval for expanded deployment, Hardcastle read it over a single evening and arrived at his conclusion before breakfast the following morning. The meeting was arranged for a Wednesday. Willoughby took the train from Newcastle again. He sat across a table from Hardcastle and 2 staff officers in a room that smelled of coal smoke and institutional carpet. Hardcastle opened the meeting by placing the file on the table between them and resting his hand on it. "Mr. Willoughby," he said, "this device of yours requires a corvette to travel at between 4 and 8 knots while towing 300 meters of weighted cable in open ocean. Are you aware of what a corvette commander's primary obligation is in a convoy escort situation?" Willoughby said he understood the concerns about speed. "His obligation," Hardcastle continued, as though Willoughby had not spoken, "is to be where the threat is. A vessel towing 300 meters of cable cannot maneuver. It cannot accelerate to intercept. It cannot depth charge a contact without first retrieving the cable, which your own documentation suggests takes 11 minutes. In 11 minutes, a U-boat moves approximately 1 kilometer. You are asking me to turn escort corvettes into slow, immobile targets in exchange for a device that has confirmed contact on what, 10 submarines? 10 confirmed, Willoughby said, with limited deployment partial implementation, and crews who received less than 2 hours of instruction. Hardcastle closed the file. The answer is no, not at this time. Willoughby returned to Newcastle. He sat at his kitchen table with his pipe and his calculations, and he thought about the 900 men dying in the Atlantic every month, while a rear admiral worried about 11-minute cable retrieval windows. He thought about this for 3 days. Then he made a telephone call. But he was not calling the Admiralty. He was calling someone who had actually fought U-boats in those convoy lanes. Someone who understood that theory and practice were two very different things. Someone who had lost men. Commander James Ferrers was 34, which in 1943 made him either young for his rank or a man who had seen enough of the war to age quickly. He had commanded a corvette in the North Atlantic for 14 months. He had lost 2 crew members to a U-boat attack in November 1942. He had filed 7 ASDIC contact reports that had produced 0 confirmed kills. When a mutual contact passed him Willoughby's technical summary in April 1943, Ferrers read it in a single sitting and then read it again. He telephoned Willoughby the following morning. "Your number's on the operational speed window," Ferrers said. 4 to 8 knots. That is exactly the speed range we maintain during fog and heavy weather in the convoy lanes, the conditions under which ASDIC is least reliable. "Yes," said Willoughby. "So you are not replacing ASDIC. You are covering the conditions where ASDIC fails." That is precisely what I have been trying to explain to people for 14 months. Ferrers had something Willoughby lacked entirely. He had the ear of Captain David Llewellyn Hughes, Senior Escort Group Commander for the Western Approaches, a man with enough operational authority to approve a formal demonstration trial without routing the request through Hardcastle's office. It was not exactly going around the system. It was as Ferrers described it to Willoughby with a straight face, using an alternative administrative pathway. They had 6 weeks, 1 demonstration. If it failed, the program was finished. Hardcastle would see to that personally. They had 4 paravanes, 2 cable drums, 1 corvette, HMS Gardenia, and a decommissioned submarine hull that the Clyde Range facility had used for previous acoustic testing. The hull was anchored at 55 meters in a section of the Firth with realistic Atlantic swell conditions. Llewellyn Hughes arranged for 8 senior officers to observe from a support vessel. Hardcastle was not among them. His deputy commander Prentice was, which was worse in its own way, because Prentice had specifically told Ferrers before the trial began that he was there to document failure, not success. May 7, 1943, 9:15 a.m. The sky was low and gray, seas running at 2 meters, wind from the northwest at 22 knots. Willoughby stood at Gardenia's stern and watched the cable drum begin to turn. The paravanes went into the water first. They were ungainly objects, cast iron and welded steel roughly the weight of a motorcycle and roughly the hydrodynamic elegance of a brick. In flat water, they would have planed immediately. In 2-meter swells, they dove-surfaced dove again, and Willoughby felt his chest tighten as he watched the depth gauge reading fluctuate. The cable followed behind them in a long curve, sinking, spreading the weighted sections, pulling it down, while the paravanes fought to hold their lateral position. For 90 seconds, the depth gauge read 38 meters. The target was at 55. Commander Prentice, standing 200 meters away on the observation vessel, was writing in his notebook. Then the swell pattern shifted. A longer, lower wave set came through from the northwest, the kind of deep Atlantic swell that had nothing to do with local wind and everything to do with a storm 2,000 kilometers away. The paravanes found their geometry in the new wave pattern. The depth gauge moved. 44 meters, 49, 53. Ferrers, standing next to Willoughby, said nothing. Neither did Willoughby. The cable drum continued to turn. Gardenia maintained 6 knots. 53 meters. 55. The contact indicator, a simple mechanical tension gauge on the cable drum, jumped. Not dramatically, Not in the way that films would later depict moments like this with sparks and noise and sudden drama. The needle moved 12 degrees to the right and held. That was all. Contact. Ferrers exhaled slowly. Willoughby looked at his watch and noted the time. Llewellyn Hughes on the observation vessel raised his binoculars toward the water as though he might see something. He saw nothing. That was the point. That was exactly the point. Over the following 40 minutes, Gardenia made 4 additional passes. Contact on 3 of them. The one miss occurred when Gardenia's speed dropped to 3.8 knots during a course adjustment just below the lower operational threshold, and the paravans lost stability for 90 seconds. Willoughby noted this. He would fix it. He already knew how. 3 of 5 passes against a stationary target in 2-meter seas, with paravans deployed by a crew that had practiced the procedure exactly twice. Llewellyn Hughes called the observation to an end at 11:40 a.m., and the support vessel came alongside Gardenia. Prentice climbed aboard and stood in front of Willoughby with his notebook closed. There was a pause that lasted approximately 4 seconds. "If you can get the miss rate below 25% in operational conditions," Prentice said finally, "I will support formal recommendation." He paused. "The paravane stability at low speed is the problem." "I know," said Willoughby. "I have already designed the modification." The formal recommendation went to the Western Approaches Command in late May 1943. Hardcastle's office received a copy as a matter of administrative protocol, by which point the decision had already been made. 12 cable systems were approved for immediate production at a Clyde area fabrication yard. 24 more were authorized contingent on operational results. The cost per unit was less than the price of a single depth charge pattern. The first operational systems reached escort groups in June 1943. And here is where Willoughby discovered that winning the argument was not the same as winning the war. The corvette captains who received the systems had not watched the May trial. They had received a technical manual, an 8-page instruction document, and a signal from command telling them this equipment would improve anti-submarine performance. Most of them read the manual once deployed the cable on their first patrol, noticed no obvious result, and spent the rest of the voyage being annoyed by the cable drum taking up space on the stern deck. Ferrers took 10 days of leave and spent it traveling between escort bases. He stood on stern decks in the rain and walked captains through paravan deployment by hand. He explained the 48-hour delayed effect. That contact damage accumulated slowly. That a boat forced to surface might do so 2 days after the cable had passed it. He explained why no immediate explosion meant the system had not failed. He explained to men who had spent 2 years training their instincts toward immediate audible, confirmable results that this weapon was silent and slow, and that silent and slow was the point. Results began arriving in July. A U-boat surfaced unexpectedly in convoy lane HX-251's wake 31 hours after the escort group had passed through. Then another in August. Then 2 within a single week in September. Both commanders describing identical symptoms: propeller fault, progressive flooding at depth, inability to dive below 70 meters. The interrogation reports that came back from prisoner processing used phrases the British intelligence officers were beginning to recognize. A vibration, early in the night. We assumed it was wave action. The Germans were not assuming anymore. By September 1943, Marine Operational Command had noted the pattern. U-boats operating in specific convoy lanes were surfacing at inexplicable rates. The damage profiles were inconsistent with depth charges. The locations were inconsistent with mines. Something was happening in those convoy lanes that German naval intelligence could not explain from the evidence available to them. They began pulling survivors harder in interrogation. They began analyzing the damage reports in detail. They began slowly and methodically to close in on the answer. And in October 1943, a captured British escort vessel taken by a surface raider in an engagement that the Admiralty would classify for 20 years was found to have a cable drum mounted on its stern and 180 meters of weighted wire still attached to it. A German naval engineer examined the equipment for 3 hours, Then he wrote a report that went directly to the office of Admiral Karl Dönitz. The report was 11 pages long. The final line read, "We now know what is killing our submarines. The question is whether we can stop it before it kills more." In Part 3, the Germans don't panic. They adapt. They begin modifying every U-boat in the Atlantic Fleet with cable deflectors, reinforced external fittings, and new operational protocols designed to neutralize everything Willoughby had built. And they nearly succeed. What follows is the moment the cable program faces its first catastrophic operational failure, and the decision Willoughby makes that nobody in the Admiralty ever fully forgave him for. By the end of Part 2, Arthur Willoughby's cable device had gone from rejected paperwork to approved Admiralty program. 12 systems deployed. U-boats surfacing in convoy lanes they had once owned. German Naval Command staring at damage reports that made no sense. And then a captured British escort vessel. A German engineer. 3 hours of examination. And a report landing on Admiral Dönitz's desk that ended with 11 words that changed everything. "We now know what is killing our submarines. The question is whether we can stop it before it kills more." Here is the number that tells you how fast the Germans moved. Between October and December 1943, the Kriegsmarine issued 847 technical modification orders to active U-boats across the Atlantic Fleet. 847 separate engineering changes pushed through in 60 days to every submarine Dönitz could reach. That is not a bureaucracy responding to a threat. That is a command structure in controlled panic. The war at sea had just entered a completely different phase, and now this was no longer a test. Admiral Karl Dönitz was not a man who lost his composure in meetings. His staff would later describe his reaction to the German engineer's October report as quiet. He read it once. He set it down. He asked 2 clarifying questions about the cable's operational depth range and the paravane spread width. Then he looked at the men around the table and said in a voice his staff described as entirely level, that they had approximately 6 weeks before the British deployed enough of these systems to make large sections of the convoy lanes operationally impossible for submerged boats. 6 weeks against a program that had already been running for a year. The German response came in 3 simultaneous directions. First, every U-boat returning to port was fitted with reinforced external antenna housings and protective collars around the propeller shaft. The 2 points the damage reports identified as most vulnerable to cable contact. The engineering was not elegant. It was fast. Welded steel collars, rough finished, added to boats that were already in port for routine maintenance. Some commanders complained the shaft collars created additional drag and reduced submerged speed by half a knot. Dönitz told them to accept it. Second, new operational orders went out to all Atlantic boats. Minimum operating depth in convoy lane areas was raised from 50 meters to 80 meters. Any escort vessel maintaining a consistent speed below 8 knots was to be treated as potentially trailing a cable system and avoided at distance rather than approached for attack position. The tactical implication was significant. It pushed U-boats deeper and further from the merchant vessels they were targeting. In the final quarter of 1943, Allied shipping losses in the North Atlantic dropped 34% compared to the same quarter in 1942. The cable was not the only reason, but it was part of the calculation. Third, and most aggressively, German naval intelligence began specifically targeting information about the cable program's production and deployment schedule. 2 intelligence attempts to place agents near the Clyde fabrication yard were disrupted by British counterintelligence in November 1943. A third attempt, through a network operating out of neutral Portugal, produced partial information about the paravane geometry before the network was rolled up in January 1944. The Germans were treating this as a priority intelligence target. That by itself told Willoughby and the DMWD exactly how seriously the device was being taken. But here is what nobody in London was saying publicly in the winter of 1943. The cable program was breaking. Not dramatically. Not in a way that produced headlines or emergency meetings at the cabinet level. It was breaking in the quiet, accumulative way that industrial programs break when they are scaled faster than the engineering assumptions that underlay them were designed to support. The original cable specification had been developed for Clyde conditions, for trial runs, for controlled deployments on vessels whose crews had been carefully briefed. The production systems now going to sea were being fitted to corvettes by dockyard workers who had received a technical circular and nothing else. Deployed by crews who understood the principle but not the tolerances. Maintained by engineers who were already stretched across a dozen other systems on the same vessel. The failure rate on Paravan depth stability, the metric Willoughby had spent 6 months of his life correcting, was climbing. Field reports from November 1943 showed that 31% of operational deployments were producing depth readings outside the effective contact window, nearly 1 in 3 systems performing below specification, and in December, a cable retrieval failure on HMS Stonecrop resulted in a fouled propeller that put the corvette out of action for 3 weeks at a moment when convoy escort numbers in the North Channel were already below requirement. Hardcastle's office noticed immediately. A formal inquiry was opened. The question being asked in the careful language of Admiralty correspondence was whether the cable program's operational failure rate represented a systemic design flaw or a training deficiency. The implication of the first answer was program cancellation. The implication of the second was Willoughby's professional responsibility. Willoughby read the inquiry notice at his kitchen table in Newcastle and sat with it for a long time. He knew the answer. He had known it since October when the first field failure reports had come back, and he had gone through them line by line. It was not the design. The design worked. It was the assumption, his assumption, built into the original specification, that crews would read and follow the Paravan depth calibration procedure every time the system was deployed. In Clyde trials, they had. On a North Atlantic corvette in December, with a crew already managing ASDIC radar depth charge systems and watch rotations in heavy weather calibration. Step 7 of a 12-step procedure was being skipped routinely because nobody had told them that Step 7 was the one that mattered most. He drafted a letter to the inquiry. He revised it 4 times. He sent it on a Thursday. It accepted full responsibility for the specification gap, proposed a revised 3-step simplified procedure that reduced calibration error to near zero, and requested 30 days to implement the revision across active deployments. It did not ask for sympathy. It asked for time. Prentice, who was now running the inquiry, gave him 21 days. March 14, 1944. North Atlantic, 54 degrees north, 22 degrees west. Convoy ON 277, 41 merchant vessels, 9 escorts. The escort group commander was Commander Thomas Alcroft, 36 years old, 12 months in the western approaches, a man who had attended Ferrer's dockside briefings twice and understood the cable system well enough to have incorporated it into his group's standard convoy procedure. 3 of his 9 escorts were running cable systems that morning, all 3 using Willoughby's revised calibration procedure. HMS Gardenia, the same corvette that had made contact in the Firth of Clyde trial, was on the convoy's port beam. German intelligence had identified ON 277 through signals intercept 2 days earlier. U-boat group Coronel 7 boats operating as a coordinated Wolfpack had been repositioned to intercept. The Wolfpack commander was Korvettenkapitän Ernst Bauer. Experienced, aggressive, the kind of commander who had made the happy time possible. He had read the new operational orders about cable towing escorts. He had the propeller shaft collars. He had the reinforced antenna housings. He intended to demonstrate that the British cable program was a problem that German engineering had already solved. Bauer's boats began approaching the convoy at 0400 on March 14th from the southwest, running at 75 meters, below the cable's operational depth range as specified in the November intelligence report. This was the correct decision based on the intelligence available to him. What the intelligence had not captured was Willoughby's October modification to the Paravan geometry. the trailing edge adjustment that extended the effective depth range from 65 meters to 88 meters. The modification that had been implemented quietly without fanfare and had not been mentioned in any document that German intelligence subsequently accessed. Bauer brought his lead boat up to 72 meters at 0423 to take a targeting solution on the convoy's lead merchant vessel. Gardenia was 400 meters to port, maintaining 6 knots, cable deployed since midnight, contact at 0431. The tension gauge moved. Gardenia's watch officer logged it and immediately signaled Allcroft. Allcroft did not break radio silence. He altered the convoy's course 15 degrees to starboard, a standard evasion pattern, and increased the escort group's ASW alert status. No depth charges. No active sonar sweep. Nothing that would tell Bauer his boat had been touched. Bauer continued his approach. He felt nothing. The contact had been on his propeller shaft collar, the new fitting welded to the shaft housing in Lorient 6 weeks earlier. The collar had done exactly what it was designed to do. It had deflected the cable. What nobody in Lorient had calculated was the stress the deflection placed on the collar's own weld seam when the cable's lateral tension pulled against it at 72 meters under the hydrodynamic load of a boat moving at 4 knots. The weld held for 19 hours. At 23:47 on March 14th, U-571 surfaced 2.1 kilometers from the convoy's rear guard, flooding in the aft ballast compartment. Propeller fault, preventing dive below 40 meters. 2 escorts were on her within 6 minutes. Bauer ordered abandon ship at 23:59. 31 of his crew of 44 were recovered from the water. 13 were not. Over the following 96 hours, 2 more Coronel boats surfaced with damage profiles that interrogators would subsequently identify as cable-related. A 4th boat, attempting to dive steeply to avoid what its commander believed was an approaching depth charge pattern, exceeded its crush depth trying to get below the cable's range and did not come back up. Wolfpack Coronel's 7 boats ended its operation against ON 277 with 0 merchant vessels sunk and 4 submarines destroyed or captured. Bauer, in British custody, was shown Willoughby's revised specification document during his interrogation. He read the section on the October depth range modification and said nothing for a considerable time. The results from ON 277 reached Western Approaches Command on March 17th. Llewellyn Hughes read it 3 times. He forwarded it to the Admiralty with a covering note that was, by the standards of Royal Navy correspondence, almost emotional. The relevant sentence read, "The performance of the cable system in this engagement suggests we have underestimated both its operational ceiling and its psychological effect on Wolfpack coordination." That was the understatement of 1944. Between January and June of that year, U-boat operational effectiveness in the North Atlantic declined by 41% compared to the same period in 1943. Cable contact was not the only factor. Long-range maritime air patrol improved radar, and the continuing intelligence advantage from broken Enigma traffic all contributed. But the cable introduced something none of those other factors could replicate: uncertainty below the surface. The knowledge, spreading through U-boat crews by word of mouth and through commanders by operational debrief, that running deep was no longer safe in the way deep had always been safe. Donitz's war diary from April 1944 contains a passage that was only declassified in 1978. It reads in translation, "Our commanders report a deterioration in crew willingness to maintain depth during convoy approach. The cable threat, real or imagined, is producing hesitation at the critical moment. This is more damaging than the physical losses." By June 1944, 23 cable systems were operational across Western Approach's escort groups. The inquiry against Willoughby had been quietly closed in February. The revised calibration procedure accepted as standard. Ferrers was mentioned in dispatches for his role in Convoy ON 277's defense. Willoughby received a letter from the Admiralty thanking him for his continued contribution to the anti-submarine program. It was signed by a junior official. He kept it anyway. The Battle of the Atlantic was not won by a single weapon or a single idea. It was won by accumulation. Radar and code breaking and aircraft and training, and the sheer grinding endurance of the men who sailed the convoy lanes month after month in weather that seemed designed specifically to break human beings. But in that accumulation, the cable played a role that the statistics alone do not capture. It changed what it meant to be deep. It turned the submarine's greatest refuge into a place of doubt. In Part 4, the final chapter. What happened to Arthur Willoughby after the war? Why does his name appear in only 4 footnotes across 3 separate official histories? And what is the single conversation he had in 1947 with an American naval engineer that quietly shaped anti-submarine warfare for the next 40 years? The man who beat the U-boat with a piece of wire did not stop there. And the story of what came next is the one that history forgot entirely. 4 parts. 4 hours of Atlantic War. An engineer nobody had heard of. A cable nobody wanted. A weapon nobody could see. From a kitchen table in Newcastle to the convoy lanes of the North Atlantic, Arthur Willoughby's device forced 10 U-boats to the surface, helped break the back of the Wolfpack system, and contributed to a 41% decline in U-boat effectiveness across the first half of 1944. The Battle of the Atlantic turned. The supply lines held. Britain survived. But here is the question Part 3 left open. What happened to the man himself? What happens to the person who saves thousands of lives with a piece of wire and receives a letter signed by a junior official? The answer is not what you expect. And it contains a final detail declassified only in 1991 that reframes everything that came before it. Because success, it turns out, has a price. And sometimes that price is silence. The war in Europe ended on May 8, 1945. Arthur Willoughby heard it on the radio in a rented room in Greenock, Scotland, where he had been living for the better part of 2 years, close enough to the Clyde fabrication yard to respond quickly when production problems arose. He had spent those 2 years solving problems that nobody officially acknowledged existed for a program that official documents described only as a miscellaneous anti-submarine development project. He was 50 years old. He had not seen his wife for 6 weeks. He took the first train back to Newcastle the following morning. His consulting retainer with the DMWD ended on June 30, 1945, terminated by standard administrative procedure along with dozens of other wartime contracts. He received no ceremony, no formal acknowledgement, no request to document his work for posterity. The DMWD itself was wound down that autumn. Its files distributed across several Admiralty departments, some classified, some archived, some, and this is the detail that would matter later, simply lost in the administrative reorganization of a government demobilizing 4 million servicemen simultaneously. Willoughby returned to the Post Office Cable Division. He was given his old grade back, assigned to a North Sea cable survey project, and resumed the work he had been doing before the war, as though the intervening years had been a brief interruption. His colleagues knew he had done something during the war. He did not discuss it. The Official Secrets Act covered the cable program until 1967, which meant that for the first 22 years of peacetime, the man who designed the system could not legally explain to anyone what he had actually accomplished. His wife Margaret would later tell their daughter that Arthur came home from the war quieter than he had left. Not damaged, she was careful to distinguish. Just quieter, as though he had learned to carry something that did not have a name and had decided carrying it silently was the only available option. Commander Ferrers was mentioned in dispatches, received the Distinguished Service Cross in 1945 for his convoy protection record, and retired from the Navy in 1952 to run a small boatyard in Devon. He and Willoughby exchanged letters twice a year until Willoughby's death. Ferrers attended the funeral. He was the only person present who knew fully what the man in the coffin had done. Rear Admiral Hardcastle retired in 1946 with full honors. His official record noted his distinguished service in convoy protection coordination. It did not mention the cable program inquiry. History in its institutional form is often generous to the people who were wrong and silent about the people who were right. Willoughby died in 1971 in Newcastle, age 76. His obituary in the local paper described him as a retired cable engineer who had worked for the post office and the Admiralty during the war. 4 lines, no specifics. His daughter, clearing his papers, found the Admiralty letter from 1944, the one thanking him for his continued contribution, signed by the junior official with the misspelled first name. She kept it. She still has it. But the legacy of what he built did not die quietly with him. It went in directions he almost certainly never imagined, and reached scales that would have staggered the man sitting at his kitchen table in 1941 with 12 pages of graph paper calculations. The towed cable principle did not end with the war. It evolved. American naval engineers working through the post-war exchange programs that transferred British wartime technical documentation to the U.S. Navy encountered the cable system concept in 1946. The initial assessment prepared by the Bureau of Ships described it as a primitive but conceptually valid approach to non-acoustic submarine detection that warranted further development with modern materials and manufacturing tolerances. The language was bureaucratically cautious. The underlying judgment was clear. This works, and we should make it work better. Here is the 1947 conversation that Part 3 promised. Willoughby, still technically bound by the Official Secrets Act, but permitted to discuss general engineering principles with cleared American counterparts under the exchange program, met a U.S. Navy engineer named Robert Caswell at a technical conference in London. Caswell was working on what would eventually become the SOSUS program, the Sound Surveillance System, a network of hydrophone arrays placed on the seabed to detect Soviet submarine movements across the North Atlantic. The systems are entirely different in their mechanics. But the conversation Caswell later described in his own memoirs, published in 1983 and largely unread outside specialist circles, was about the same underlying question that Willoughby had been answering since 1941. How do you find a submarine that does not want to be found? Caswell wrote that the British engineers' framing of the problem, stop trying to listen for it and start putting things in its path, influenced his own thinking about passive detection architecture in ways he found difficult to quantify precisely, but impossible to dismiss. SOSUS became operational in 1961. At its peak, it covered the entire North Atlantic, tracking Soviet submarines, with a consistency that acoustic technology alone could not have achieved. The system monitored Soviet submarine movements throughout the Cold War, contributing to naval deterrence calculations that arguably prevented escalation during some of the most dangerous moments of that era. The number of lives it saved in the sense of conflicts it helped prevent from becoming active is genuinely impossible to count. The conceptual thread running from Willoughby's kitchen table to those seabed hydrophone arrays is not a straight line. It bends through Caswell's memoirs and through a dozen other engineers' contributions. But it is there. The towed array sonar systems that NATO surface vessels use today, the kind that trail behind frigates in exercises and deployments across the world's oceans, operate on a principle that would be recognizable to anyone who understood Willoughby's 1942 design. Not identical. The technology is vastly more sophisticated, incorporating digital signal processing, computer analysis, and frequency ranges Willoughby had no means to work with. But the fundamental geometry, a line of sensors trailed behind a moving vessel to cover the water column. The vessel is passing through is the same idea executed differently, rooted in the same recognition that the ocean's three-dimensional space can be covered by something you trail through it rather than something you point at it. 14 NATO member states currently operate towed array sonar systems. The technology has been continuously in service in evolving forms since the 1950s. Willoughby's contribution to that lineage appears in 0 official histories of towed array development. But here is the lesson that matters more than the technology. The deepest lesson of this story is not technical. The technical lesson is interesting. Simple solutions outperform complex ones in harsh operating environments. Physical detection can succeed where acoustic detection fails. But it is not the point. The point is what the story reveals about how good ideas move or fail to move through institutions under pressure. Willoughby was rejected 3 times before he found the DMWD. Not because his idea was wrong. It was not wrong. He was rejected because the people who rejected him were evaluating his proposal against a mental model of anti-submarine warfare that had no category for physical passive detection. The idea was not incomprehensible to them. It was simply outside the framework through which they understood the problem. This is not stupidity. It is the normal condition of expertise. The more deeply you understand a domain in a specific way, the harder it becomes to see the domain differently. The Second World War produced several examples of this pattern. Barnes-Wallace's bouncing bomb was rejected 8 times before it was tested. Percy Spencer's observation that radar equipment melted a chocolate bar in his pocket was initially treated as a curiosity before it became the microwave oven. Frank Whittle spent 6 years trying to convince the Air Ministry that jet propulsion was worth funding. In each case, the idea was not rejected because the institution was malicious or incompetent. It was rejected because institutions are built to optimize what already works. And the person with the new idea is asking them to redirect resources toward something that might work instead. That is a genuinely difficult ask during peacetime, during wartime, with men dying and budgets stretched and every existing system demanding maintenance and personnel. It is almost impossible. Except when it is not. Except when someone finds the DMWD equivalent, the side door. The department with the deliberately forgettable name that exists precisely because the main departments cannot process what they cannot categorize. Every organization of sufficient size has a version of this problem. Everyone needs a version of the DMWD. The question is whether they build it before the crisis or only during it. And now the detail that was classified until 1991. The detail that Willoughby never knew. When the German engineer examined the captured cable system in October 1943 and wrote his 11-page report to Dönitz, he included an appendix that was separated from the main report during the post-war archival process and filed under a different classification category. The appendix was declassified as part of a German Naval archive release in 1991 and translated into English by a researcher at the Imperial War Museum who was working on an entirely different project. The appendix contained the German engineer's assessment of the cable system's design quality. He had examined Willoughby's paravane geometry, the cable weighting distribution, the calibration procedure. His professional conclusion, written for an audience of Kriegsmarine engineers, was that the British system was unsophisticated in its materials and manufacturing, but exceptional in its conceptual design. The depth coverage geometry, he wrote, was elegant. The decision to use the vessel's own forward motion as the deployment energy source, requiring no additional power, no additional mechanism, no additional failure point, was in his assessment the work of someone who understood the sea. He did not know the designer's name. The British had been careful about that. But he described the mind behind the system as that of an engineer who thought the way the ocean thinks, which is perhaps the most precise description of Arthur Willoughby that anyone ever wrote. Willoughby never read it. He died 20 years before it was declassified. His daughter, informed of its existence by the Imperial War Museum researcher in 1993, was asked if she would like a copy. She said yes. She framed it. It hangs in her home in Northumberland next to the Admiralty letter with the misspelled name. From a post office cable engineer with 12 pages of mathematics and 3 committee rejections to 10 U-boats forced to the surface, to a conceptual lineage running through SOSUS and towed array sonar into the naval doctrine of 14 nations. Arthur Willoughby proved that the most powerful weapon is sometimes the one that requires no power at all. He proved that the right answer and the accepted answer are not always the same answer, and that the distance between them is measured not in intelligence, but in persistence. Across the 4 parts of this story, one number matters more than any other. The merchant sailors who crossed the Atlantic in the winter of 1943 and arrived. We cannot count them precisely. We know they existed. We know the cable was part of why. The ocean keeps no records. The wire left no mark. But somewhere in the North Atlantic, at depths where light does not reach, the physics that Arthur Willoughby calculated at his kitchen table are still true. Weight falls, Wire spreads. The water does not care whether anyone remembers who worked it out. History should. If you know a story like this, an invention, a person, a decision that changed everything and received nothing, share it in the comments. These are the stories that fall through the official record and survive only because someone thought they were worth telling. This has been one of hundreds from the Second World War alone. Because the most important history is almost never the history that gets the statue. The man who beat the U-boat with a piece of wire never got his statue, but the wire worked.